Hi everyone, I'm Fraser Cain. I'm the publisher of Universe Today. I've been a space and astronomy journalist for over 20 years. We do a lot of content here on our YouTube channel, and that generates a lot of questions. And I like to answer them. So go ahead, wherever you are across my channel, if a question pops in your brain, just write it down. I will sometimes just answer them in the chat, and sometimes I will gather them up and I'll answer them here. Now, we record this show live every Monday at 5 p.m. Pacific time. So if you want to show up and ask your questions live, ask follow-up questions, chat with the rest of the community, definitely join us every 5 p.m. Monday here on the YouTube channel. And there should be a link to the next upcoming event somewhere around. Of course, every week we put these codes up in the video, and the code is essentially a short name for the question that you thought was the best. And so if you're watching this video or watch them all, and then the question that you like the best, just type that in as part of your question, or you can just use the one word, and that will tell us which of the questions you thought was great. And this week we got the most votes for Jan Ware's The Question About Sending Dinosaurs to Space. Obviously, that was pretty cool. So congratulations to Jan, and I hope my answer was adequate. We just did an episode which we called The Big Q, and it was all about James Webb questions. I tried to consolidate all of the questions that I've got about James Webb into one mega episode. But I also said that, of course, this is going to generate new questions, all the stuff on the edges of the things that I didn't answer. And what a surprise. We got a million questions more about James Webb. So I'm going to tackle some James Webb questions first, and then we'll get into more general questions next. So there's always time codes throughout the episode. So if you want to jump to any part, if you've had enough James Webb questions, go ahead and jump ahead. Mose Artificer. Can we please know how the color is reckoned? Thank you, James Webb Space Telescope team. All right. There is like a short answer and a long answer to this question. So the short answer is that James Webb has 29 narrowband filters that it can use to produce images in different wavelengths, and then those images are turned into a full color image. The long answer is to just talk about color images in astrophotography in general. And so I'm just going to sort of give you the short version of this as well. When you just have like a regular photograph, there's three colors that come together. There's red, blue, and green. And so you can mix those three colors, red, blue, and green, and that gives you a full color image that roughly approximates what your eye would see. And so if you went out and you took a blue filter, and so you essentially only allowed the blue filter in of a tree, and then a green filter, only let the green in, and then a red filter, and only let the red light in, and then you merge those three images together, you would get what looks like a tree, a full color image of the tree, and yet each of the separate panes would look like full color. And your camera on your phone is doing this. If you've got a DSLR camera, it's doing some version of that. All photographs that you look at are actually separate images that are merged together. And so when you look at pictures that come from the Hubble Space Telescope, for example, Hubble has a whole bunch of filters that are on board, and it has dozens of these filters. And so when an astronomer is looking to take an image, they will chart out which of the filters they want to use when they take a picture. And the filters are designed to show off very specific kinds of elements or chemicals or gases or things like that in the object that they're looking at. And so a common example is they might use a hydrogen alpha filter. And so they're essentially looking to let through the light that is released by hydrogen in a certain excited state, hot hydrogen, the kind of stuff that you would find in a newly forming nebula that contains stars, right? And so they would want an image in hydrogen, and then it would be a black and white image that is taken, and then it is produced on the telescope, and then that data is sent back down to Earth, and you've got this black and white image. But you know, as a scientist, that in fact, this is where there is more hydrogen that is giving off radiation that we can see. Another one that they might ask for is oxygen. And so you're looking for the presence of oxygen in a nebula. And oxygen is a heavier element, and you would expect to see different regions of the nebula are producing oxygen. And then you might look for sulfur, which is another heavier element, and it's going to be in different parts of the nebula and producing different signals. And so you have these three versions. Each one is black and white. They are very useful scientifically to tell you where these regions of hydrogen and oxygen and sulfur are in the nebula. And then you go into Photoshop and you take the three images and you say, the hydrogen one is red, the oxygen one is blue, and the sulfur one is green. You merge them together and you get a full color image. And that process that I just described to you is what you see when you look at, say, your favorite astrophotography. If you're looking at the Pillars of Creation or the Horsehead Nebula or images of Andromeda or almost anything, you're seeing multiple narrowband filters that produced single photographs that were then merged in Photoshop or computer or whatever to produce a full color image. So like all images that you've seen are done this way because telescopes allow us to see things that our eyeballs can't see. So how do you make a full color image of the regions of a nebula that are glowing in infrared, the regions that are in visible light, and the regions that are in ultraviolet? Your eye can't see that. There is no way to say, like, what would that really look like? It would look like a amorphous kind of gray blur to your eyes. But the fact is that it is scientifically very interesting in those different wavelengths. And so they're put together in a way that allows you visually to see information in that nebula. But it is all sort of it's kind of an artistic impression of what's really going on there because our eyes can't see it. James Webb is an infrared telescope. And on the NIRCam, which is one of the instruments on board James Webb, it has 29 filters that allow it, same thing, to see different varieties of infrared, different wavelengths, and block out the rest. And so when scientists are going to be working with James Webb, they're going to be trying to study different parts. And you can think about infrared as different levels of heat. And they're going to be looking at these different wavelengths of infrared. And that will tell them different information about where the dust is being blocked, where the new planets are, where galaxies are, all that. And they're going to have these black and white images that are coming off the telescope. One is on near infrared at a certain wavelength. Another one might be at near infrared at a certain wavelength. And another one's going to be mid infrared at a different wavelength. And you've got three separate images that are going to give you three different pieces of information. And then in the computer, you can put one to red, one to blue, and one to green, and you can make a full color image. So James Webb will be looking at things that the human eye just cannot see. There is no way for us to be able to observe them. So we have to deal with this fact that it is false color. It is a creation that is done in a computer to be able to give some kind of visual representation of what is being shown. And so when you go into looking at these images, just remember that what you're seeing is beautiful because there's a lot of complexity, a lot of information, a lot of different regions that are doing different kinds of things. And it's very meaningful scientifically. And that is how the colors are reckoned. Future Fraser here. We're doing the edit on this episode. And after I'd finished my question, I saw a similar answer given by Dr. Becky about what it means for Webb to see in full color. And she gave an amazing answer, way better than mine. And so I want to link you over to what Becky had to say in kind of addition to what I said about space telescopes producing color. But the gist of it that I thought was just so clever was that Webb, because it's an infrared telescope, it is looking at colors that have been redshifted really far away. And so when it looks at a galaxy that is just 1 billion years after the Big Bang, that galaxy emitted its light in full color, in visible light. But those visible light have been redshifted so that now they're in shades of infrared. But if you take the one wavelength of infrared and then a second wavelength of infrared and a third wavelength, and those match up the visible light colors that galaxy was in the beginning, you are essentially recreating what that galaxy would have looked like in full color. But now, because it's been redshifted so far into the infrared, we can't see it. And I think that's a perfect way to describe it as well. So definitely check out, we'll put a link to Dr. Becky's episode and you can watch that here. SPAK-USA. Will we have uncensored access to these pictures, or will the owners only allow the pictures they feel should be released? The rule with the Hubble Space Telescope and James Webb is that the images are kept just for the scientists for the first year, and then they're released to the public onto the archive. And so anybody who wants is allowed to look through the images that are a year old and dig into whatever they want. And so, like, why is this information not just dumped right onto the internet immediately? And the reason is because a scientist has requested time on James Webb. They've said, we want to look in this very specific region for this very specific amount of time using these very specific filters, wavelengths, instruments on board James Webb. Let's say they're looking for Planet 9. They gather all their data. And so if that data was immediately published out onto the internet, then everyone else could look at it and go, you just found Planet 9. Let's write a paper about it. Let's do a news story about it. And the information would get out before the scientists who are doing the research, who want to be able to publish information about Planet 9, have had a chance to do their work. And so they get an advance access to the data that they requested. But then after the year, all the information is publicly available. And so it's a nice balance in that if you're going to be doing science, you want to be able to get access to the data. You want to be able to have some time to digest the data, to do your research, to be able to publish the information, get it into a journal, whatever. And then anyone who wants can go through all of the information afterwards. And there's some really interesting science that gets done with this archival data. Recently, astronomers found thousands of asteroids in archival data. So they just went and ran a computer through a ton of images taken by Hubble for all kinds of purposes, and it turned up tons and tons of asteroids, many of which had never been seen before. And you actually get to name them after yourself or your friends if you want, or your favorite space journalists. So it's a nice balance, but nobody's hiding anything. It's just that there is a lead time for the scientists to be able to work with the data. But in other cases, data is dumped just immediately onto the internet, like with the Mars rovers or the Vera Rubin Observatory. The data is going to be dumped. And generally, the difference is if it's just a mission that is just gathering tons and tons of data with all of its instruments, and that information is just being dumped out onto the internet, versus a telescope that you have to request very specific time to pick one very specific target and be able to have a chance to analyze the data before it's all just publicly available to everybody and anyone can scoop you on your discovery. So that's how it works. AJ Taha. How does James Webb avoid strikes by space debris, etc.? It doesn't. But fortunately, there isn't much stuff out there. You have to be worried in a low Earth orbit environment where we've got potentially hundreds of thousands of satellites and pieces of garbage and debris and paint flecks and everything buzzing around the low Earth orbit environment. But once you're out where James Webb is, you're far away from anything that's producing debris. You've got the occasional pieces of sand that are floating through space, and some of them are going to impact James Webb, and they're maybe cause some damage, but most likely not. But it's just a matter of just assuming that space is really big, and these chances of these objects hitting the telescope and causing any damage are really low, and it's a risk they're willing to take. Future Fraser here. We were just doing the edit on this episode, and it made sense to talk about the meteorite strike that actually did hit James Webb. The news came out just on Thursday after we'd already recorded the question show, and I wasn't aware. Anyway, so it turns out that Webb has been struck 5 times by micrometeorites, pieces of dust. And this is expected, but it was struck by a fairly large piece, about 0.1 millimeters, which sounds really tiny, and yet it was moving many kilometers per second and caused a more significant piece of damage to one of Webb's 18 mirror segments. The damage is noticeable, but it is not going to cause a significant impact on the science capabilities of the instrument. And so I think we're going to be able to see much more of this over time throughout the lifetime of the observatory. And this is one of the things that NASA has taken into account. But the 0.1 was surprisingly large, and so I don't think we're going to see many more objects that are that big or bigger into the future. PG Antioch. How is James Webb pointed? Is the telescope always attached to the sun shield at the same angle? Right. So when you think about James Webb, right, you've got the sun shield on the one side, which is blocking the sun, the moon, and the Earth. And so only one hemisphere of the sky is available to James Webb. But when you actually look at the telescope, it's on this little gimbal that can turn up and down, but not very much. And then it also has reaction wheels on board that will allow it to rotate around. And so it can access, so when you think about, like, if you've got the sun shield is up here, James Webb is here, it can turn, so it can see stuff that's about 5% off perpendicular to the sun. And it can also go down to about, so it can go 85% to 135%. And then it can turn itself around. And so there's like this kind of ribbon in the sky that it can view, but it can't look exactly opposite to the sun. And then James Webb will be going around the sun over the course of an entire year. And so it will be able to, in one half of the year, be able to observe the constellations that are opposite to the sun. And then in the other half of the year, it'll be able to observe the constellations that are opposite to the sun when it's on the other side of the sun. So it won't be able to see the entire sky. It won't be able to see the stuff that is directly opposite to the sun. So it can't go below the 45 degrees off, directly opposite to the sun. So that's a region that James Webb will never be able to look. Sort of, because the Earth and the sun goes a little higher and a little lower than the sun based on the Earth's, anyway, roughly. Darren Jones, could dark matter be regionally detectable in the universe and we cannot detect it as there isn't any in our local area? Yeah, this is a possibility. Dark matter, astronomers still aren't sure whether the particles are really big or they're really small, or whether they're actually primordial mass black holes, or they're not even particles at all. They're just gravity working in a way that we don't understand with general relativity and Newtonian mechanics. One of the possibilities is that it could be a particle, and that particle is very heavy. Like it could be a primordial mass black hole. And so we could have a black hole here in the solar system that is orbiting around the sun, and it would be really hard to spot. But occasionally, particles would fall into this black hole, and they would release this tiny little burst of gamma radiation, and we could detect these blasts of gamma radiation because it's relatively close to us compared to things that are really far away. So that's one idea of how we might be able to detect dark matter here in the solar system. Another possibility would be that maybe dark matter can fall into the sun or into planets. And when it is in these gravity wells and very dense, it can annihilate with itself and release excess energy, heat up the planet more than it should normally be. And so just by measuring the temperature of the planet compared to other places, other planets, you might get a sense that there is dark matter hiding inside the planet. So there are like dozens of ideas for what dark matter could be, and just as many ideas for how to test them. Some we could find them right here on Earth. In other cases, we might not be able to find them without doing giant surveys across the entire universe. Right now, we don't have enough information. More questions in a second, but first I'd like to thank our patrons: Joseph Koch, Sylvester Ratout, Douglas Wilkinson, Evans, ADG, Medenkale, and the rest of our 1,019 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. And I'll also remove all the ads from the Universe Today website for life. Nikhil Kumar, what are the observational clues that help confirm dark energy, dark matter indirectly, if any? Do we know for sure that it exists, or is it a smart guess? The way science works, ideally, is that you have a fact. And then from that fact, you develop some kind of hypothesis. And then from the hypothesis, you have an experiment. And the experiment allows you to disqualify your hypothesis. And then you go back to the beginning and you come up with another hypothesis, and then you disqualify it. So let me give you an example. So let's say you're driving down the road and you hear a sound coming from your car that is different, unusual, not what you would normally expect. Maybe a pinging sound coming out of your car. So you now have a fact. There is a pinging sound coming out of your car. The next thing for you to do is you're going to come up with a hypothesis. You're going to say, uh-oh, there's a rock in my tire. And so you stop the car and you check the tires and there's no rocks. And you keep driving and there's still a pinging sound. You go, uh-oh, okay, maybe there's a problem with my engine. And so you stop the car at a mechanic. The mechanic takes your engine apart, puts it all back together, everything's fine, and the pinging sound is still there. And you could just go through this process forever until you find the thing that is causing the pinging sound. So that is the process. And so dark matter and dark energy have gone through this exact same process, which is that there are these facts that have been discovered. And for dark energy, the fact is that when you observe supernova, which are really far away, and a certain kind of supernova always give off the same amount of energy. And so when you see it, you know how far away that supernova is, because you know how bright it is intrinsically, and you see how bright it is, and that tells you how far away it is. And when astronomers observed all these different supernova, they found that they were farther away than they should be. And so they're farther away than the expansion of the universe would lead you to believe they should be. And so over time, the universe, the expansion of the universe is accelerating. So now you've got these facts. The fact is the universe is expanding more quickly than astronomers were expecting. So then you enter the domain of the hypothesis. What's causing it? What is this? Has it always been the same over time? In the early universe, was the increase growing more slowly and now it's speeding up? Or has it always been a constant acceleration on the expansion of the universe? Is it evenly distributed? You're getting the same amount of expansion in a small region and a different amount of expansion in a bigger region? Does it only push to the left? You have all of these questions that you're trying to gather up and these hypotheses of what could be causing it. And astronomers currently, as it relates to dark energy, are just in the measuring phase. They don't have any, they have lots of ideas, they have lots of hypotheses, but they haven't been able to disprove them to the point that they're left with one that seems to be right. Dark matter is a little more further along. We've got tons and tons of observations, big and small, and astronomers have just as many hypotheses, and they're attempting to rule them out one after the other. And we're in the middle of that process. So it's not that it's a guess. It is the astronomical equivalent of your car making a weird sound. And it is. You have another person sit in the car with you. They hear the sound too. So there's no question that the sound is coming from the car. And, it's not like your friend's going to yeah, I do hear the sound, but how do we know there's a sound? Are we just guessing? Is this just something we've made up? Is this like our version of God? No, there's a sound. So dark matter, it is the equivalent. Same thing with dark energy. And that's where we are currently in the state. We're in the middle of trying to figure out what it is. And if we could fast forward 20 years, 50 years, 100 years, we might find out what the answer is. But right now, we don't know. My brother comes. Why does the Earth have so much water when the moon doesn't? The proto-Earth and Theia, which collided, that made up the moon, formed at the same time, so it doesn't make sense to me. Well, it shouldn't make sense to you because it's a bit of a mystery. Now, where did the Earth's water come from? The answer is we don't know, because there shouldn't be any water on the Earth. The problem is that you've got the sun, and the sun is releasing out a tremendous amount of radiation, of energy. And if you have a surface, say you took a block of ice and you just sat it out in space, the heat from the sun would melt the ice, but because it's in the vacuum of space, the ice would just go straight to gas. It would sublimate. And so the ice cube that you put in space would grow a tail, and you would have made a little mini comet. And then all of the ice would disappear, and then it would be gone. And space would be dry as a bone again. And yet the Earth has oceans in a region of the solar system that shouldn't have. If you go out to halfway in the asteroid belt, then if you put a block of ice out in space, it would be able to just sit there. But once you get inside the asteroid belt, you get comets from ice cubes. And so where did this water come from? We don't know. There's a bunch of possibilities. The most commonly believed possibility is that it was comets. The comets rained down on the Earth over long periods of time and were able to deliver the water. And the Earth is protected by a thick atmosphere. It's protected by a magnetosphere. And so as the sun tried to heat up the water on the Earth and try to blow it away into space, the atmosphere was able to keep the Earth cool enough that it was able to hold on to its water. But the moon doesn't have an atmosphere. And so even if this, whatever process happened on the Earth happened on the moon, then the sun was drying off this water, causing it to be like a comet off the moon. Whenever a comet would strike the moon, you'd have this blob of ice sitting on the moon, and then the radiation from the sun would blast it away, and so the moon would remain dry. But we do know there's actually a surprising amount of water on the moon. Some is mixed in with the regolith, and not a lot, like a bottle of water in every cubic meter of regolith, but still not none. And it does look like there's water at the poles of the moon, where the sunlight can't get into the shadows of some of these craters. And so without that sunlight hitting the ice, it doesn't sublimate away. So where did the water come from? We don't know. Maybe it came from comets. Maybe it just came in place. Maybe it came from asteroids. Is there no water on the moon? Is there some water on the moon? We still don't quite know. And that's sort of why one of the purposes of the Artemis missions is to go back to the moon, to the places where there could be frozen water on the surface of the moon, to try to understand the history. So, you're asking the kind of question that geologists, planetary scientists would love to know the answer to. Nifty. They might have found life in 800 million year old salt crystals. Does this mean that panspermia is inevitable? I haven't seen this specific research, but I believe it, that, we know there was life on Earth for billions of years. So to find life that was captured by salt crystals seems feasible to me. But this idea of panspermia, this idea that you've got asteroid impacts happening on one planet and it's blasting material to space, and then the material is landing on another planet, and maybe you've got life trapped inside salt crystals and is being blasted off Earth and landing on Mars, and then some process is melting away the salt, and now the life has a chance to live on Mars. Yeah, obviously we can't say that it's inevitable because we have no evidence that there is any life on any other worlds but Earth. But the whole purpose of the rovers and the Europa Clipper and all these upcoming missions is to search for some evidence of life anywhere else in the solar system. And if we do find life on these worlds, then we're going to want to perform some kind of genetic analysis and figure out when we shared a common ancestor. And if it is indeed that we shared a common ancestor with cyanobacteria that is 800 million years old, then the most likely possibility is that it was through panspermia, that this material hitchhiked from an asteroid impact to go from one planet to the other. And so it means that we might find life across the solar system, and it's all related. And then it doesn't give us any more information about whether or not there's life on any other star system in the Milky Way, because it seems that it can naturally move from planet to planet inside a single star system. So it sounds exciting, and it would be very cool to find life on Mars, whatever, but it would be as exciting to find out that the life evolved independently and we don't share a common ancestor. So I love the idea of panspermia, that life just gets from world to world. Life finds a way, and I would love to hear the first actual discovery of something that can confirm it. Sias. Hey Fraser, is it really correct to refer to the Big Bang as a past event? Since we're undergoing inflation, isn't the bang technically still ongoing? So I need to clarify the language a little bit here. So when you say that we are undergoing inflation, the universe is getting less dense over time, but that is very different from the period of inflation that happened very shortly after the Big Bang. That lasted for a very short period of time, and then regular expansion, essentially the momentum of that initial expansion took over, and now we are just coasting, plus dark energy is accelerating the expansion of the universe to whatever the final form is going to be. So when people think about the Big Bang, they think about that initial period of rapid expansion, of rapid de-densification of the universe, and yet we are still coasting. And so, if you're riding your bicycle and you pedal your bicycle really hard and you speed up and then you coast, are you still getting the momentum from when you pedaled, but you're not still pedaling? So to take that analogy, King Petway, what is the best telescope to see Jupiter? A Dobsonian telescope is the best way to see Jupiter. So, people always want to buy telescopes because they think they're going to see all kinds of amazing things in the night sky. But really, for most people, the thing you're going to be looking at is the moon, Jupiter, Saturn, Mars, maybe Venus. And those are sort of like the really cool, bright objects that you can see. And the telescope that I always recommend is the Dobsonian. It's very easy to use, very quick to move to a new location. You can point it at some direction and be able to see the object that you want to see. So if you know where Jupiter is in the sky right now, you look it in the sky, you take your Dobsonian, you look through it, and you can see Jupiter. But if you can get to some nice dark skies and you can know your way around the sky, then you can use that Dobsonian to go and look at nebulae and star clusters and galaxies and all kinds of cool stuff. So it's really my favorite beginning telescope. They are relatively inexpensive to the go-to telescopes, the ones that are just all automatic. A Dobsonian, like a 6-inch Dobsonian is going to cost you about $300. An 8-inch is going to cost you about $500. Don't go bigger than an 8-inch. You'll be tempted to go to like a 10-inch or 12-inch. Don't do it. They give you a little bit better review, but they make for a really difficult to use telescope. So get a 6-inch or an 8-inch Dobsonian telescope, set it up. You'll be really happy with it, and it'll carry you for years and years and years. Eka Ramdani. If we mapped the cosmic microwave background from, say, Andromeda Galaxy, would we see regions that we never seen before? Yes, but you can be 1 kilometer away from somebody else, and you're looking at a different cosmic microwave background radiation than they are, because you're essentially seeing the moment that the universe was releasing these first photons when it became transparent. And the region that you see is different from the region that I see. I'll give you an analogy, right? Like when you look at the moon and you see this really cool ring around the moon, that's because there's crystals in the air that are of a certain shape, and they are refracting the light that is coming from the moon back at you. And so you're seeing this rainbow around the moon. But if we are several meters apart, we are actually seeing different rings. We're not seeing the same ring. You're seeing the ones that is made up by millions of little ice crystals in the air, and I'm seeing one that is made up by completely different millions of little ice crystals in the air that are refracting the light directly towards my eyeballs. And so the same thing goes with the cosmic microwave background. If you are in one spot on Earth, you're seeing one version of the cosmic microwave background, and the people in Andromeda are seeing a different one. But it wouldn't let you, say, map out regions of the universe that the other person can't see, because we've mapped out the cosmic microwave background, and there isn't much to see beyond very slight temperature variations that map out to the large-scale structures of the universe that are similar today. And so you would see regions of hotter and colder, but you wouldn't necessarily see anything vastly different. S. Lynch, MD. Why is it that we can still see the light from 13 billion years ago when we were in a much closer location to its origin, not passed us by? I'm not sure I exactly understand the question, so I'm just going to ramble in the area, and hopefully the answer that you're looking for will pop out of what I'm saying. When we look out into space, we are looking back in time. The farther we look, the further back in time we go. And the farthest that we can see is essentially the beginning of time, 13.8 billion years ago, give or take. And that is when the cosmic microwave background radiation was released. Now, where we are and where that region is and where that region was at the beginning of time, we're actually relatively close together, but you get the expansion of the universe over time that has carried us away from those regions. But that light has still taken 13.8 billion years to make its journey from when it was released from the cosmic microwave background to us. And where we are today is the cosmic microwave background for somebody else in the universe. If you just take the light that was released from this exact spot of the universe and let it travel for 13.8 billion years, there's going to be someone who will be able to see the light from those photons that have been traveling for 13.8 billion years. Even though we see the Earth and the Milky Way, etc., they just see minor fluctuations in the cosmic microwave background. They see the beginning of the universe. POV Dave. Hey Fraser, happy Pride. What are some good nonprofits that help promote diversity in STEM? I don't know about promoting diversity specifically in STEM, but it's interesting. Like, I look at the viewers of our channel and we get 95% male, sometimes 90% male in some of the questions. So there's definitely not diversity in the kinds of people that are watching YouTube videos about space. And, you know, I really try. If you look at, say, the Weekly Space Hangout, and thanks to Nancy, like, most of the journalists on the show are women. We have a lot of people of color on the show. If you look at the kind of guests that I have here on my interviews, I try to bring on a lot of female astronomers, cosmologists, people of color, etc. And so, you know, I don't really know, like, what's the best way that we can overall increase diversity in STEM. But I think that having role models that show people that it's a thing that they can do, that it's perfectly normal to see a Black woman speaking about cosmology for an hour. And we kind of have to normalize that. So I feel like my part in this is to just put these people on the stage and let them just do their thing. And the rest will happen over time as more and more people see more people that look like them doing the kinds of things professionally that they find interesting. But it's a tricky problem, and I hope that people are able to solve it. All right, those were all the questions this week. Of course, we've got a bunch about James Webb. Keep them coming. You know, who knows how many we'll get a chance to answer. Remember that we're going to be finally seeing the first pictures from James Webb on July the 12th. So it's getting closer and closer. We do the show live every Monday at 5 p.m. Pacific time. So if you want to join live, definitely do that. Otherwise, just post your question anywhere in any of the videos and I will answer them here. See you next week. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links so that you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all my videos are also available in handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. I'll put a link in the show notes. Thanks to all the moderators, and a special thanks as always to Chad Weber, Nancy Graziano, and Anton Poznikov.